I'm seeing like your screen.
I could see
I don't
you.
see the PowerPoint. Okay, there we go. Look at that. Here we are, webinar Wednesday. Jim over here going to be answering questions. Chris is in the back running the camera stuff. Looks like we worked out all the gremlins and bugs, and we're going to get off on the right foot here today. So hopefully everybody can hear me.
Who are you?
Yeah. Oh yeah. I'm John, by the way. Yeah. Hey, thanks for reminding me. It's early. Um, Today is week 3. Jim ran you through week 2. Everybody has figured out that slide bar over there. You can ask the questions. Let's keep that going today, and then you can slide the screen up and down to open up the screen, make me real small so you can focus on the work at hand. Today we will be in our take-home book. All right, everybody got that right in a download. If you want to make a note, the pages you're going to be using for the most part today will be page 48, 51, and 55, just as a heads up. So makes it a little easier when you're trying to do these the problems that we're going to get into. Today, again, it's going to be, we're going to take one of the myths out of our industry right here in the get-go. We'll talk through some near boiler components. We'll talk a little bit about primary, secondary, and then we're going to get into root cause troubleshooting. So that's where you'll be doing the work. So I have in front of me, I have a calculator, or you can use your cell phone. I got a pen, I got a piece of paper, and that TACO catalog so that I can take and start to do this root cause troubleshooting. If you also have in front of you your page with the pipe sizing and the BTU with a 20, 30, and 40 degree delta, that would also be helpful. But so let's get this rolling. Okay, first off, we always start with questions from week 2. If anyone has questions from week 2, you can shoot them into Jim right now, and we'll get those answered. Static pressure in a boiler system, what is it? What does it do? How does it work? That's what we're going to talk about. Circulator, the position of a circulator in a system, and how does it affect what goes on inside the pipe, the area that we can never see, what goes on inside the pipe. We're going to hit primary, secondary piping. We're going to simplify it. I hopefully simplify it and make it to the point where it's common terms for you. We'll talk a little bit about choosing between zone valves and circulators with the amount of jobs that we go on. Sometimes we see some jobs that maybe we would have leaned a little bit towards circulators. Others we see where maybe we would lean towards zone valves, and we'll just give you some, just some food for thought. There is no right or wrong answer there, but we'll give you some food for thought, and then we're going to get into that root cause troubleshooting, and we're going to do it from 2 perspectives. We're going to try to put you as best we can in a boiler room, and then we're going to put you on the other end of a phone with a service technician. He's going to feed you all the information. You're going to have to draw out the system that he's feeding you the information for, so that you'll be on both sides of it. Okay? So static pressure within a building. We get calls all the time. What size circulator do I need? The building on the left here, you can see it's a 1-story building. The building on the right there, let's call that a 5-story building. We always get the phone call, hey, I got a 5-story building. I need to know what circulator I need for that building. And it's a myth in our industry, and I'm going to ask this question. Looking at those 2 buildings, if I have a boiler room and the same amount of pipe wrapping around the 1-story building, and I have a boiler room, I have the same amount of pipe wrapping around the 5-story building, but the 5-story building is vertical. Would I have 2 different circulators for those type applications? You can fire an answer off to Jim, please. And I don't know if I said it, but good morning to everybody. Yeah, good morning, and thank you for coming back. Jim didn't bust you too much last week, so your fingers are still working. It's good.
Speed date last week.
Anybody answering?
We have 1 answer.
And it is?
Actually, 2 have just come in.
Go ahead.
3 have come in. Everybody's saying no, not necessarily. Same circ, doesn't matter.
Okay, same circuit, doesn't matter. Okay, and That's the correct answer. So I'm just going to slide these circulators in here. So the height of the building really doesn't change the size of our circulator. It's the amount of pipe that is hooked to that circuit that changes the size of the circulator. And we're going to dive into that a little bit here today to help you size circulators, because we're going to be doing that. So over here on the left-hand side of the column, okay, this is the head side. This is the flow side. And that's going to be important to know, because we're going to be diving into this a lot today. So basically, if I'm just going to use this circulator as my boiler plant for this one-story building, and let's say I wrap all the way around this building, and that total pipe length is, I don't know, call it 300 feet. I need to take that 300 feet, and we're going to get into this. You're going to multiply that by 1.5, and then multiply that by 0.04, and that's going to give me the head loss of that heat circuit. So if I were to look at this building, and this would be my boiler plant, and I have the same 300 feet of pipe going around that building, and I just have to overcome the resistance of that pipe, it's going to be the same calculation. 300 times 1.5 times 0.04, and it's going to give me the head loss of that heat circuit. So to lift the water from the lowest point in the boiler to the highest point in the system, that's static pressure. That deals with your feeder and everything along those lines, your feeder, your expansion tank, and how they work together, and the ability of a boiler to hold the pressure. Okay, so these two systems, they're going to use the same size circulator because they have the same amount of pipe footage hooked to them. The building on the left, that could work easily with our standard, 12 psi feed valve and 12 psi expansion tank that come standard from your distribution channel. The building on the right, now we may have to change that. So let's talk about that a little bit here. So static pressure refers to the weight of the water in a system. Static pressure does not affect pump capacity, feet of head, has nothing to do with height of the building. 1 psi has the ability to elevate water 2.31 feet or 28 inches. Okay, so we're going to rely on the water feed valve, pressure reducing valve, feed valve, whatever everybody calls it, something different, but the feeder to the boiler, we're going to rely on that to overcome the height of the building and supply us with the static pressure we need in the system to allow us to flow the water through the piping. And then it's our circulator's responsibility to be able to overcome the hydraulic resistance in that pipe, right? It's like a friction loss in that pipe. So here's a system, right? Think of it as a Ferris wheel. The person at the top is going to make its way to the bottom. And the weight of the chair and the person and everything is going to work its way to the bottom. As it's working to the bottom, it's taking the person that's at the bottom of the Ferris wheel and it's lifting them up. So basically, our circulator is a centrifugal pump. All we're doing is changing pressures. On the outlet side of the circulator is where we really want to change the pressure. So when we turn this circulator on, we want to see the positive side of the circulator, which is this side leaving the circulator, and we want to lift the water up. And as we're lifting that water up, this water is pushing down. So it is just like that Ferris wheel right next door. So we don't need this gigantic circulator, just like this Ferris wheel doesn't need a gigantic motor in order to make that happen. We just have to get the thing flowing. And with static pressure, which is our goal here, 1 psi, again, 2.31 feet of lift we get out of that. So 12 psi, which is our standard feed valve that comes from pretty much every manufacturer out there. 12 psi times 2.31 equals 27.72 feet. So let's call it 28 feet. So out of the box, your expansion tank, and out of the box, your boiler feed valve, it has the ability to lift water from the boiler 28 feet up. So that covers majority of our, two-story homes that we work in every single day, and that's where the number 12 comes from. So pretty simple. A lot of guys didn't know why or how that number, why is everything set at 12 psi? this explains why, right? We can get from our boiler plant in the basement to the second floor, no problem. So 18.5 times 0.43. So 0.43, that's going to be a multiplier you can use. So if you measure your lowest point in your boiler to the highest point of water, you know, whether it's an air handler or baseboard on this floor right here, and that's 18.5 feet, we're going to take that and we're going to multiply it by 0.43. This is just going to give you a you know, cheat sheet, so to speak. That's 7.95 psi, and then you will always add 4 psi to that. So basically, we're calling this 8 psi. We're going to add 4 to it, and that's going to give us our 12 psi. So a lot of different ways you can look at this, but the bottom line is we need to make sure that the pressure within our system has the ability to elevate the water to the height that we need in order to support water flow at the highest point. Okay, we never want to allow the air bubbles in the system, excuse me, which will always be in the system. You're always going to have small bubbles in the system, but we never want to allow those bubbles to have a party on the second or third floor and create a service call for you. You have to go out there and purge the system. So location, location, location. By putting the circulators on the supply, this will give you the advantage of taking advantage of the positive pressure of the circulator to push against the resistance in your heating system, whatever your heat emitter is, by pumping away from the expansion tank. So here would be our feed valve. This would be our expansion tank. We are out here pumping away from that. So we're going to take the backside will stay at normal pressure. The positive side will increase, usually it's 4 to 5 psi, and that will go up and around, overcome the head resistance of that heat circuit, back into the boiler to be reheated, and back out to make its journey again. So with all those parts and pieces right here in this area, they're all working as a system with the boiler and with the circulator and its location. So you may have heard the term out there, Dan Holohan has always had the term out there, pumping away. You're pumping away from that expansion tank, you're pumping away from that boiler. And, you know, it's hard because majority of everything you see out there, cast iron wise, that's, you know, older equipment, they used to come packaged, you know, right here on the boiler, on the return, and then you would pump into the boiler, then you would pump into the expansion tank, then you would send it out to the system. And it worked in most homes, but if you have a problem job, and we'll show you an example of it later, what it might look like, it's important to have that circulator in the right location and allow these items to do their job. Putting the pressure, the static pressure on the boiler that we need, your adjustment is here. Having the air pressure correct on the bottom side of this expansion tank to match what your feeder is putting in, and then having a good air scrubber to you know, get those little micro bubbles out of the system so that we eliminate as many as we can within the system. So that's really what our goal is here. And here we are. We're going to show you basically when you purchase an expansion tank here, we happen to have a cutaway. This is FlexCon. We're the FlexCon guys. So I purchased this. I take it out of the box. It should have 12 psi of air on the bottom side of this unit. And what that does is when it's not tied to the system, it has the rubber diaphragm pressed right up against the metal. So we have a feed valve here, take-off feed valve, backflow preventer, set at 12 psi. When I turn on the main, the water is going to come in. This is going to reduce the house pressure to 12 psi. We're going to come in, we're going to go in, we're going to fill the system, we're going to purge the air out of the system, and at the same time that's filling up, we now put 12 psi of water pressure on top of this rubber diaphragm, and it pushes this rubber diaphragm down a little bit. So now I have 12 psi on the bottom of the expansion tank, 12 psi on the water side of the expansion tank. And that's what it would look like sitting idle at 12 psi. So then the home needs heat, And as I heat up the water, the system will expand. Let's say we have 10, 12, 15, 20 gallons of water in there, depending on the size of the boiler and what type of boiler it is. And then what will happen is as I expand that water, it has the ability to push down on this rubber diaphragm, and it will live down here. And I still have my 12 PSI on the top and 12 PSI on the bottom, and I have a good system. And as the system cools off, the rubber diaphragm will go back up into a higher position, and the rubber diaphragm will be in the tank. It will have no additional stress on it. It will be working the way it was designed to work. But what happens sometimes, what we see in the field is I'll leave my expansion tank at 12 PSI. But because I'm higher than that, 18 to 20 feet, I elevate the system pressure, the operating pressure of the system with my boiler feed valve. Let's say I don't know, you may like it at, 15, 18 PSI, whatever you like. And that's fine. You can put it at 15 PSI. It's not going to hurt anything. But I have to adjust the air side of the expansion tank before I fill the system. I cannot adjust this when it's on the system. I cannot take the pressure of the air side when it's on the system. It all has to be done when it's off the system. And this is just expansion tanks in general. Even if I'm putting it on a hot water heater, if I have a potable expansion tank going onto a water heater, I need to match the system pressure of the home. Here on the hydronic heating side, I need to match the system pressure with the air pressure on the bottom side of this tank in order to allow that diaphragm tank to work properly. So that's how the diaphragm tank works. We normally don't get to see inside of the tank. There's a cutaway. That's what it looks like. That's how it works. So if you're going to elevate the pressure within your system for whatever reason, height of the home, whatever it may be, make sure you adjust the air cushion side of the expansion tank before you install it on the system and marry the two up so you have a great working system. We good so far, Jim?
Absolutely.
All right. This is just a brief overview of what it would look like. So here, if I just take and if I were to measure, my distance from my lowest point of water in the boiler to the highest point within the building. So on here, I'm saying it's 45 feet. 45 times 0.43, that's going to give me 19.4 PSI. And then I'm always going to add an additional 4 PSI to it. I would have to operate that system at 23 PSI. And we break it down, whatever your height of the building is, it will tell you what your operating pressure should be. So here, we're all the way up to 25 feet and still with the, typical setting on a feed valve, we're within 3 PSI. Here we're 15 feet, we're at 11 PSI. So, right around that 20-foot mark is where you're going to be, starting to say to yourself, do I need to change the system static pressure? And again, no matter what I do here and here, it has no effect on this. No effect on the circulator sizing.
All right, a couple of good questions that just came in.
Shoot.
Any downsides for laying the tank on its side? Shouldn't be.
Yeah, there's all different ones, right? So we have the round ones, there's flat ones, they're on their side. The diaphragm works this way. It shouldn't. What I get nervous about is I see these, just hanging out here on its side, but they're not supported.
Right.
So I get nervous about it from that standpoint. From an operational standpoint, it should not matter because 12 PSI, both sides are full. We're not, putting it anywhere. Normally, though, this is a small one. If I see a 60 or a 30 on its side and it's only being supported by this fitting, I'm not so comfortable because if the diaphragm were to fail and I fill this with water, it's going to be a tremendous amount of weight there.
Yeah.
That would be the only downside. What else you got?
And just clear up, 4 PSI, is that a buffer? I know the answer. But...
Right. So I'm going to leave that question because the next 3 slides will address that 4 PSI.
Awesome.
Great questions. Thank you. Keep them coming. So pump toward the expansion tank. That's a question, right? You must create a pressure differential. That's all we do with a circulator. Here we have a 007E. All we're looking to do is create a pressure differential from the inlet side to the outlet side. We have to create that pressure differential to make the water move through our system. Okay? So here's a system. And this system is going to be a standard 12 PSI system. Just so you know, your boiler right here would be a takeoff in here somewhere. We just didn't put it there because there's going to be a lot going on this slide, which you'll see in a few minutes. So what this is telling us here is that, I'm going to fill all this up, and then I'll run through it with you. Okay, so this is your standard system. It is a 12 PSI system. So the expansion tank and the feed valve are married up. Everything is good, right? So from our boiler room to the highest point in the home is 18.5 feet, which is going to lose us about 8 PSI. So when we get to the highest level in the house, running across the highest level in the house, we only have 4 PSI left here at the top. And then we drop down and come back to the boiler to be reheated and sent back out by the circulator. And that's what it looks like when the system is off. What I'd like you to tell me now is, let's answer this in a 4-part. What happens to this number when I turn that circulator on? So you're going to answer that first. You're going to answer what happens to this number, what happens to this number, and what happens to this number when I activate this circulator and turn it on. Currently, my pressure differential across my circulator is 0, 12, and 12. What happens when I turn this on? Answer 1, answer 2, answer 3, answer 4. I want to see if we have some brave souls out there, Jim, that are going to dive in and answer these questions. Don't give any names. Don't give any names.
Well, one comment was if the tank is in the wrong position, I guess this is going back to whether it's upside, if it's straight up
Yep.
or sideways,
Yep.
that you could trap air inside the tank and lead to corrosion.
Yeah, theoretically you could.
Yeah.
Yeah.
That's
This is the method that the manufacturer want, because here's our air elimination.
right.
But we see them in all different positions, and I'm not saying it's right or wrong.
Right.
And definitely corrosion can happen. Oxygen corrosion happens in, hydraulic separators, right? With the square, and you don't have an air can on top, and you rot them out. So it can definitely happen. This is the method. I just get nervous when I see them sideways and they're not supported.
So a couple of answers coming in that
All right,
nothing
shoot.
changes.
Okay.
Whoa, things jumped around a bit. Number 2 same, number 3 same, number 4 down.
Okay.
12 PSI after pump should not change because that is the point of no pressure change. All right.
All right. Good.
That gentleman's been here a few times, so you should
Good.
know it by now.
All right. So we just turned that circulator on. The front side of the circulator stays at 12. The 18 feet up, that doesn't change. So we still have that 8 PSI pressure drop. Somebody shoot me an answer. What happens here? And what happens here? Even if it's a guess, we're good with that. Tick, 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 tick. We need some Jeopardy music.
We do have an answer.
Go ahead. What do you got?
0.
0. That is a 4 PSI pressure drop across the circulator. The expansion tank stays at 12 PSI. Up top is going to go to 0 because we need to create a pressure differential across the circulator. So the point of no pressure drop really is out here. So by pumping into the expansion tank, the circulator still has to create a pressure differential. So on this type application, this is like if it were on the return type application, right? Our boiler would be right here between the expansion tank and the outlet of the circulator. That would mean the circulator on the return, we're pulling the differential from the back side of the circulator. So in the previous picture, we had 4 PSI up here, but we created a 4 PSI differential with the circulator coming on, which creates a problem because now we are at 0 PSI at the highest point. So if you have a job like this where you've been out there several times for bleeding of air time after time after time, most guys will go back and they will put an air can somewhere along this highest run. And if I'm going to zero, when that circulator first comes on, if I drop this a little bit below zero, realistically, that air can has the ability to draw air, more air into the system. So just something to be aware of. This will be more of like, it's a historically, you're going there 2 times a year to purge air out. Take a look at the piping. Take a look at the circulator location. If it is on the return, don't go in there, and say, oh my God, we got to repipe this whole system. Maybe you can elevate the pressures, remove the expansion tank, elevate the pressures within the system. Let's try to keep a little bit of pressure up here at the highest point, preferably 4. So maybe you raise your whole system up to 16 PSI, and we're still going to create the pressure differential on the backside, but we won't be going to a 0 PSI at the highest point. That may be a Band-Aid for that system until it hits its mature age and gets replaced, right? So just an option. So let's look at it now. Let's say you did repipe it, or you were going to install a new boiler. So now we have the boiler location will be, again, before the expansion tank over here. We go through our air separation, feed valve, point of no pressure drop right here, right? Go into the inlet side of the circulator, the outlet side of the circulator, still have the same 18.5, 8 PSI drop. Let's fill this in. So circulator's off, 0 pressure drop. System tank is at 12, system is at 12, return side is at 12, high side is at 4 PSI. All right, same thing. Answer number 1 will be here. We know this is going to stay the same. We'll skip that one. Answer number 2 will be what happens here. Answer number 3 will be what happens here. So tell me what happens to the 12 on the positive side of the circulator, the 4 at the top of the system, the 12 at the back side of the circulator.
I can hear the typing.
Yeah, me too. Crickets. Interesting.
Yeah.
Okay.
One gentleman saying on the back side of the circulator, 0.
0.
Yeah.
Okay, that's not a good thing.
No.
That'd be a time to replace the circulator at some point.
One gentleman saying everything stays the same.
Okay.
One gentleman says 1 and 1 same, 2 same. Wait a second. 1 same, 2 same, 3. I'm thinking that they're all thinking everything stays
Stays the same. All right, well, let's turn the circulator on. All right, circulator is now on. Circulator creates that 4 PSI differential. Tank stays at 12 PSI. Outlet side of the circulator, it was 12, add 4 to that, it becomes 16. We climb the hill. Backside the circulator, because we're at the point of no pressure drop, stays the same. That's where our feeder, expansion tank, and everything is. Even though we're going to lose 8 PSI climbing that hill to the 2nd or 3rd floor, to 18 feet, 18 and a half feet up, we've actually increased our pressure up here at the highest point. So if we do have air bubbles in there, as long as we're moving water, if you remember what we've talked about velocity, as long as we're moving water at 2 feet per second, we have the ability to grab the air on the way up and the air on the way down, the air across the highest point, and bring it back to our air separation right here and eliminate it from the system and keep that system as air-free as possible. So this is the pumping away method. Again, Dan Holohan has really taken that term and made it real in our industry, and people are understanding it. And, it's really probably the best method that you can use when you're piping your system. So we good there, Jim? Everybody good?
Yep.
Okay, great. Okay, so we are going to switch gears now. We're going to get into primary, secondary. And we like to try to make this as simple as we possibly can. So what's going on between the 2 T's? Well, several things can go on between the 2 T's. So the connection between the 2 T's is very short. usually 4 to 8 pipe diameters. If you can keep it closer to 4, that's even better. And the reason for that is the pressure drop in that piece of pipe should be very low. That gives us the ability to manipulate the water flow within those two T's. And depending on the flow rates of the primary and secondary pumps, we can move water backward, forward, or it can sit still. So that may sound crazy, but you may go into a job like this where there's this one gigantic boiler. Your goal is to replace this with multiples. If, let's say that's the job, you're going to find somewhere on the return to cut it, somewhere on the supply to cut it. And this is going to be your easiest boiler removal ever. So that boiler is now gone. We have the supply pipe right here that we just cut. We have the return pipe right here that we just cut. And think of it like this. I'm going to take this little pointer, I'm going to come over, I'm going to drop down, and I'm going to tie this to this. So now my supply and return piping are tied together. Somewhere I'm going to take two closely spaced T's and make them 4 pipe diameters apart. And then I'm going to come out with a header and tie in my multiple boilers. So this is what it would look like. I tied them together. And this has a max of 12. That's going to be dictated by the pipe size. But if you keep 4 pipe diameters, outside dimension of these two T's, come off with the equal size header as this piping right here. And you're going to be able to tie these boilers directly into those headers and create a multiple boiler type application. So if you are going to do this multiple boiler type application, your goal is to take your first boiler, and that's your first boiler into the system, and you would like to take your return for that boiler and make it last out. And what that has the ability to do is that gives the boilers each the opportunity to work the same amount of run hours and see same temperatures and things like that. If I did this boiler here as the first in and first out, it would do majority of the work because these other boilers would see a preheated water going back to them, so they would not run as hard, maybe modulate, if it's modulating equipment, modulate at different rates. And your number one boiler, let's say it's cast iron, it would see the greatest delta T. So we just do a reverse return on the 3 boilers going in and the 3 boilers going out for supplies and returns. So that's a form of primary, secondary with multiple boilers. Now let's get into something that may be a little more realistic for what you do on a daily basis. So at the bottom of this PowerPoint photo here, this is a boiler. And week 1, week 2, universal hydronic formula. I'm just going to assume a 20-degree delta T. Who can tell me the size of this boiler based upon the flow rates that you see right here on the boiler piping? And if you need to remind yourself of the universal hydronic formula, that would be page 48.
We have a high achiever here today.
Yeah? What do we got?
He nailed it.
Okay, good. So he took 20-degree delta T, multiplied that by 500, equals 10,000. 10,000 times 14 equals 140,000 BTU boiler. So that's what we currently have here. So most condensing boilers will come with a circulator. This circulator only function in life is to move the required amount of water across this heat exchangers of the boiler every minute that it's on. Okay? So we have 3 circulators here, and we are going to call them 7-gallon per minute circulators. Each one has the ability to move 7 gallons a minute. In this scenario, there is only one circulator that is on. So this circulator is pulling 7 gallons of water off of this header and sending it out to the heat emitter, through the heat emitters, and coming back into the return. What is happening right now between these closely spaced T's right here? Everything is on. What's going on between the T's? Is water sitting still? Is water bypassing? Is water going in reverse?
Everything's on, all 3 circs.
Only one circ's on. Only one circ's on. We got 7 GPM in our header system. And here, I'll clarify a few numbers for everybody. Okay, there's our flow rate in our system, which theoretically that is our secondary, primary system. Anytime you have water that flows through a T like this, that's called your primary circuit. Anytime you have the water that comes out of the bowl of the T, this is the secondary circuit. It sounds backwards, so what we do here, try to simplify things, we call this the boiler circuit, and we call this the system circuit. That way there's no confusion. What do we got, Jim? What's going on between the two T's? Anybody?
We got 7 GPM in reverse, 7-gallon bypass, but yeah, he's got it.
Okay, here we go. So the boiler needs 14 gallons per minute. The boiler will get 14 gallons per minute. Does not matter where it comes from. So what's going on currently is 7 gallons per minute is going in reverse. So 14 gallons a minute is coming in. We're heating that water up in the boiler. Comes out of the top of the heat exchanger here, goes up to this T at that point because we can manipulate the water between these two closely spaced T's. And because they're closely spaced, low pressure drop. So that gives us the ability to do what we need to do. 7 gallons of water is going out to the system. 7 gallons of water is going backwards. 7 gallons of water is coming back from the return, and they mix here to deliver 14 gallons of water back to the heat exchanger to be reheated and sent back out. Now, next question for you. That's a condensing modulating boiler. How is it working right now? Is it ramping up? Is it ramping down? Is it staying the same? Based on what you're seeing right here with the piping, how should that boiler be reacting? As I look to Jim for answers. He's got a heck of a smile on, guys. I don't know what you guys are saying to him, but he's been smiling for like an hour.
So you got 2 answers coming in, ramping down, running half capacity.
Right. It's going to slow down. And the reason it's slowing down, just so everybody's aware, most condensing boilers will have a return sensor on them. So if we're putting hot water out here, I'm not going to say a temperature, hot water out here, and we're coming back with a little bit cooler water, but 50% of the water going back down this return is hot water from the supply. We're mixing it. So the return sensor will see that, and it will say to the boiler, reduce your input. That boiler right now has no idea whatsoever how many zones are calling. It just knows it sees warmer water coming back, it's going to reduce its flow rate. So that is the first thing that can happen as we step through this. I say the first thing. This is one thing that can happen between those two closely spaced T's. Next up, it's a little colder out. So now we have 2 circulators on, 7 gallons apiece. So that means we have 14 gallons a minute for the system to circulate water through the heat emitters. What's going on right here?
Our high achievers crushing it today. He got it, but I'm going to wait for a couple other people before I say it.
Oh, I gave it up. 0. Nothing's going on. Nothing is going on because, and here's the reason why, we have 14 gallons of flow in our system heating our home, and the boiler is requiring 14 gallons a minute. So as I send 14 gallons out of the boiler, all 14 gallons are going out here. It's being split 7 and 7. They're going out through their heat emitters, coming back to the return, and then dropping back down into the boiler at 14 GPM, which means we have 0 flow taking place between the two closely spaced T's. Another reason we need those T's close together so we can manipulate the flow or no flow because of the low pressure drop between those two T's. And here we go again. Now it's cold out. We have all 3 circulators on. We're trying to support the load within the home. So that means I have 7 times 3, 21 gallons in my supply header, 21 gallons in my return header. What's going on right here?
So we got 7 going forward.
Yep.
One gentleman saying there's a -7.
Okay.
And another gentleman, 1/3 of return bypassing.
Yeah, he's right.
Yep.
Yep. Okay, good. Excellent. So what does that look like? We are going to bypass 7 gallons. The boiler, remember, this circulator, its only function in life is to move 14 GPM across this heat exchanger. It knows nothing about what's going up here. That's the other reason for closely spaced T's. You never have 2 circulators see each other unless they're circulators that are exact, like 2 009s or 2 007s, and they got to be bolted flange to flange. So this is a hydraulic separation point. This circulator does not see these circulators, nor does it care what they're doing. So in this application, they're moving 21 gallons a minute. This circulator doesn't care that they're moving 21 gallons a minute. It only needs 14. So it takes its 14, pulls it across the heat exchanger, heats it, sends it back out here. So 7 gallons are bypassing. In this scenario right here, what's happening to my supply temperature? I'm going to give you a number now. I am leaving the boiler. I'm at 160 degrees leaving the boiler. I'm at 140 degrees coming back. Is my supply temperature equal to my boiler supply pipe? And if not, where do you think it lands? Just throw a number out there. You don't have to be spot on. Is it 160?
We got one gentleman going for a 150.
So a mix, right?
170, 150.
170 would be going the opposite direction because we're putting 140 degree water, let's call it 140 degree water, and we're bypassing 7 gallons. So, you know, a third, as the one gentleman said earlier, a third of the water coming back to mix with the boiler water, which is 160, we're going to cool that water off a little bit. So if you have, like, let's say on a design day and your boiler is marginal, you may struggle a little bit on temperature here for that. So just ask this question. This is your home. You're paying for the BTUs that are being supported by this boiler. It's cold outside. All 3 circulators are on. Boiler circulator is on. Boiler is running full speed. This is your house. You're paying for the heat. What do you want going on between those 2 T's right now when all 3 circulators are on? And I am not giving you a flow rate out here. So you just tell me what you want going on between those T's when the whole house is up and running. Is that smoke I see coming out of your computer, Jim, or is that, yeah?
No, they're getting it.
Okay, good. What are they saying?
0.
They want nothing. And the reason they want nothing is because they're paying for the heat. That means every, whatever, natural gas, whatever it is, propane you're putting in here, every ounce of it you put in there, you want that to heat your home on the coldest day of the year. So great, everybody's on the same page. Okay, is that primary, secondary? We need quick fingers here on this one. Quick fingers. Primary, secondary, yes or no?
Oh, interesting. So 50% say yes, 50% say no.
Okay.
Now we're starting to get more yes.
Here we go. So, large diameter pipe, supply, return, boiler, 10 GPM out here, 10 GPM out there, 20 to the boiler. I'm going to say that this is 4 to 8 pipe diameters apart. And what's happening right now between those 2 T's? Forward, reverse, or sitting still, and what's my rate? Sorry, Jim, I hear you clicking away over there. Jim's, if you've seen what we look at, Jim is looking at a screen that's like, you know, not even a ½ inch tall and maybe 4 or 5 inches wide. So he's going blind over there today.
So we got 10 reverse, 10, 10, 10 going back.
Beautiful.
A little still.
Excellent. All right, so we got that one. Here we go. Primary, secondary, yes or no? Since it's the same diagram, I'll say yes, this is primary, secondary. What's going on between the 2 T's?
Oh man, these guys are fast.
Yeah.
0, nothing.
All right, great. Nothing. All right, same diagram. This is primary, secondary. What's going on between the two T's?
Here it comes. 10 forward, 10 back.
Oh, easy, 10 back. 10 forward, bypassing 10 GPM. Agreed. All right, quick fingers here. Let's get 5 answers in, and then we'll move to the next one. Is that primary, secondary?
Yes.
Okay, got 5 of them. So yes, moose antlers can be primary, secondary. Here's our boiler. Here's our 2 closely spaced T's. Here's our supply, our return moose antler. Here's our supply moose antler. Okay, so that can happen. Is that primary, secondary?
Yes.
Okay, yes it is. Does anybody see anything wrong with that picture? Since we're the Takeo guys.
Yeah. Wrong color pumps.
Primary, secondary, boiler into the bowl of the T. Oh, look at that. They used our flanges because they're good. But man, oh man, I got to have some fun with it. Okay, we showed you one picture earlier. Is this primary, secondary? And is it piped properly? Primary, secondary, answer that first, and then is it piped properly? I'll take a yes, yes, a yes, no, a no, no, whatever you got.
Resounding yeses. One yes with a question mark. So
Okay, well,
right.
good.
He's not confident.
Okay, so right here, closely spaced T's, primary, secondary. So let's follow this boiler, okay? Boiler supply. First boiler in, right? Boiler return. Last boiler out. So this is piped correctly, primary, secondary, reverse return on the boilers. Great system. Okay, good. All right, so we have 2 boilers. And they are piped primary, secondary. Without counting this primary, secondary connection point, how many primary, secondaries do you see in that system?
Oh, our high achiever is on fire today.
What do we got?
Ooh, interesting. All right. I got 2 guys for 4, 1 guy for 5. Couple people saying 3.
Okay.
2.
They all make sense. 2 doesn't make sense. Everything else does. So in this system, we have a primary, secondary connection here. That's for our boilers, and they are reverse return. So our boiler supply will go this way. Our hottest takeoff is primary, secondary. We have a circulator right here, and we have a circulator on what we're going to call right here the hot loop. Okay? So hottest takeoff first for hot water, primary, secondary connection. We come around through, pumping away from the expansion tank. We get to our baseboard circuit. It has its own circulator. Again, primary, secondary connections. So by taking BTU off here, by taking BTU off here, we will get some cascading of temperatures. So this line, this whole hot loop right here, would have to be sized properly to carry the full BTU load of both of these boilers. We will continue down, and we have another primary, secondary connection here going to a snow melt system. And then we leave that, again, with some cascading of temperatures, and we come over to an injection panel, which basically is a primary, secondary connection. We're just doing it with a relay and a couple of circulators. So 1, 2, 3, 4, and 5 for guys that look at this as a primary, secondary connection. So all those answers are good. The one answer, 2, we're a little beyond 2, but the rest of them, they're all good answers. So
John,
yeah,
I'm sorry to interrupt you there.
go.
Gentlemen want to know, so you do need reverse return since you have extra pumps?
Not because of the extra pumps. Reverse return, we would always do reverse return on the boiler, so they do the same amount of work. So this boiler right here, you can see is the second one in, but is the first one out. So that's just to make sure we keep the boilers operating at the same temperature and somewhere around the same input rate if they modulate. These are, looks like oil boilers here, cast iron oil boilers, so they're on and off, but we'll have them at the same temperatures. They'll be more even on temperature. The reason we're doing here in this type of system, this is a multiple boiler hot circuit. I call this a hot circuit, and then we're teeing off with closely spaced tees for primary, secondary. So this circulator right here is not seen by the boiler circulators because of this hydraulic separation point. This circulator here is not seen by this circulator because of this hydraulic separation point, and so on and so on. Okay, everybody's good? Here we go.
What
do you got?
was thinking there was a lot of air separators on there.
Let's go back.
I think he's getting confused with the circulators out there.
Come on, fat fingers. I think they're flow valves, Jim. Right here, they do look like air separators. They're flow valves.
Oh, I got you.
Yep, they're flow valves. Yep, flow checks. Good catch. Paying attention, baby. That's awesome. Good. Okay, so Jim will talk probably more about this in week 4, so I'm not going to spend a lot of time here, but I take a note here. Just the Honeywell standard valve, 3/4 CV, 3.5. Write this down. Consider that 35,000 BTU, and here consider it 100,000 BTU just for CV ratings. You may have to do some troubleshooting related to zone valves. So that's just for your information. So let me just back up. I want to make sure everybody gets that. 35,000, 100,000. Here we go. Circulators versus zone valves, right? This is an age-old discussion. You can go on to any different webinar you want, and they'll give you all different reasons and types and so on and so on. And again, there's no really right or wrong answer here. We have both. We have multiple models of both. No right or wrong answer. But what we find in the field is there's kind of an area where whether you're a sales guy, whether you're a technician, whether you spec boilers or not, we kind of find it right in that 110 to 130,000 BTU area is where we start to look at it being a zone valve job or a circulator job. And the reason behind that number is that we look at circulator curves. And based on circulator curves and circulator capability, I don't think I ever want to have a zone valve system with greater than a 0010 circulator because of velocity. And if I get to anything larger than that, I'd have a bypass, and it just creates, a lot more items to put in there. So strictly geared around velocity and noise. If I only have one heat circuit open and it's my master bedroom at night and I have a 0010 downstairs, I'm good. If I have a 0012 downstairs, I'm probably sounding like I got a freight train coming through my bedroom when the heat circuit is on and everything else is off. So that's kind of the break point that we look at. If someone asks us, we go in that 110 to 130,000 BTU range, and we say, you know what, below 130,000 BTU, it probably is a good application for zone valves. So this application back here, I got a 007E, I got a 3/4 heat circuit, a 3/4 heat circuit. Going back to week 1, we know 40,000 BTU, 40,000 BTU. I got an 80,000 BTU system. Great. I could do this with circulators, and if I just went with a typical AC 007, or I went with a 3-speed circulator and put it on the no callback speed of high, my delta T from my supply to my return and the water going back to the boiler is probably going to be single digits its whole life. So we're not really designing systems around a single digit delta T. So that's why we would go with a one circulator with multiple zone valves. Once I get beyond 4 zones, maybe a 5th zone valve, maybe, depending on the application. But majority of the time, once I get to 4, I've kind of used up the ability of the standard circulator that comes with the boiler. So this is where, this bald head gets its ideas from is I look at the ability of what this can do, the ability of what each one of these heat circuits can do, and that kind of helps me make a decision as to what's going to be the right appliance for the application. Once I get to 4 zones, I almost automatically start thinking circulators. But I just wanted to give you a BTU range to think about. Go ahead, Jim.
So one gentleman said, in that scenario of a lot of zones, a big pump, would a VT or delta T circulator fix that?
If it hits the numbers, yes. If it hits the numbers. But again, we got to look at that curve. The VT is the only one out there that does it off of temperature. I love that thought process. But anybody who's doing AC circulators still, or is starting to get into the ECM world, which is just more efficient and quieter and a lot of benefits here, the capability of this 10 feet ahead out to 8.25 GPM, so that's 82,500 BTU. If I have 4 heat circuits here, 40, 80, 120, 160, 82,500 at full capacity. Yes, we could go to a 0010 and we could get up to those numbers, but if this comes with the boiler, more than likely it's being used in the system. So we're just pointing it out, and again, we're not saying one way is right or wrong, but when we go on a job that's noisy, the first thing we look at is it a zone valve job or is it a circulator job, and what is the BTU of the appliance? And if I have a 230,000 BTU or 250,000 BTU appliance, it came with a 007, no doubt about it. It came with a 007, and then I have a wall of zone valves, and I'm there, for insufficient heat, let's call it, because I got 8 zones off of that, which BTU-wise, it marries up. But I don't have enough circulator capacity. But the manufacturer gave you that. Well, they did. But if you look deeper into the manual, they gave you that because they want it piped in primary, secondary. And yes, this has the ability to move the water across that cast iron boiler heat exchanger at 2 to 3 feet ahead at 25, 26, 27 GPM, and it will handle the boiler. But then you would have to address the system side separately. So keep that in mind. This is just food for thought. And here's I always like to give backups of where these answers come from. So here's our 007 E curve, 10 feet ahead, out to 8.25 GPM, right down there. So call it 83,000 BTU worth of energy I can get out of that circulator. And then I can get more flow out of it as I get out on this curve, but I would have to make sure that I'm under 10 feet of head. So if I had a system with 6 feet ahead, yeah, I could get all the way out there to, a little over 11 gallons per minute, 110, 115,000 BTU. If I have a system with short heat circuits, but there's a lot of them, and we're in the 5 feet ahead range, yeah, we can get all the way out here to 120,000 BTU. So this is how you match them up and figure out, what's the best way to go. And then here, typical 007, we're going to be looking at line number 5. So line number 5 is right here. We can go all the way out 25 GPM at, 0 feet ahead. If I got a 6-foot head system, I can go all the way over here. I'm going to be in the 150,000 BTU range. So just food for thought. We want you to make sure that, you're putting in the right appliance for the application. And as you're out there thinking and selling and trying to, get a homeowner to put a new piece of equipment in, is it going to be zone valves? Is it going to be circulators? And go from there.
This wasn't a question. Well, he's coming in with his answers. In general, let's say he's got a 16-unit apartment building, and there's twin boilers in there, and there's 16 Takeo 571s.
Mm-hmm.
His question was, how is this working?
Yeah.
So my response to him was, well, what's the net of the boilers? What size circulators there? Really, we should ask him how it's piped and everything like that.
Yeah, what size piping? And this speaks to the fact that hydronic heating is the most forgiving heat medium that anyone will work with. If that was a hot air system, forget about it, right? He'd be under duct sized or whatever. But because of load shifting, because of zone valves opening and closing at different times, all the different apartment using different temperatures or whatever, the little circulators will overcome.
Right.
Will it work? Is it working? Yes. Take it out and redo it? No, we're not saying that. But we're saying if you have a problem, we want you to understand how to get to the root cause of that problem. So he may have zero problems, but if he had a system installed properly, he might take his energy cost down dramatically.
Right. This looks like it's a big system.
Yeah.
Twin 300,000s.
Yeah, nice.
And it's got a good size B&G circulator on it. But again, we don't know how they pipe it primary, secondary. I would assume they did.
You would think a two-boiler system. Yeah, right, exactly. Because if that B&G is pushing through a take ozone valve, it's probably making a little noise.
Interesting question or a statement.
Go ahead.
This gentleman's got trouble with a low BTU load in a high performance home, small as well. Is there any way around buffer tank?
Yeah, no, not really. I mean, even these circulators will turn down on pressure. You could look at the VT, but 4 feet ahead is the lowest on the VT.
Right.
So, you'd have to really look at the circulator curves on a job like that. So even here, this runs at 10 feet ahead. It will adjust its flow rate. Let me just back up one slide. There's a 007 East curve, and the 0015, we do have a low setting on the 0015, which would get you down, up to max of 85 feet. I don't know if that fits into his BTU load, but you could set that on low, and on low, you'll run down in here 4 or 5 feet ahead on a 0015. So at 1 GPM, you could match the load a little bit better. But on micro circuits, as we call them, usually a buffer tank is the real answer. You create that flywheel of energy in that buffer tank and pull off of that before you turn the boiler on with the big circulators. Okay, so great conversations going on here.
Yeah, this is fun.
This is good. Now we're going to get into figuring out head loss and so on and so on. So if you have page 48, this is where we're going to be looking. You have a 20,000 BTU heat circuit. That 28,000 BTU heat circuit, I'm going to assume a 20-degree delta T. So I've done my math here for you, and I have given you, it is a 2 gallon per minute flow rate. There is 40 feet of baseboard and 125 feet of pipe and fittings, which means we have a total heat circuit. So if I look at this boiler right here, we're telling you where you're leaving here, we're going out, we're going through 40 feet of baseboard, all the way around, back to the return piping back here, and that whole circuit is 165 feet. My question to you, based on the information, which is the head loss copper pipe calculation on page 48, it says easy way estimating. What is the head loss of that heat circuit?
High achiever is crushing it today.
Okay. Must be Jim Fry.
You should ask the gentleman if he slept at a Holiday Inn last night.
Yeah. How many answers have you gotten?
One.
Only one.
Just our high achiever. Here they come.
All right.
Yeah, they're getting it.
All right. So, for those who got it, wonderful. For those who didn't, this is how we do it. We take 165, that's our total heat circuit. We multiply that by 1.5. The 1.5, that is our full length. And then the 5 is a 50% fudge factor to account for elbows, valves, and such throughout that heat circuit. So multiply that by 1.5, and then we're going to multiply that by 0.04. And that's going to equal 9.9 feet of head. So the 0.4, that's looking at our flow rates, velocities through that pipe, and we come up with 9.9 feet of head. Is everyone comfortable doing that? Because this is going to be a theme of what we're going to be doing here going forward. Okay, so let me get rid of this and this. That will stay the same. It's not on your screen, it'll be on the board here. Just to make sure everybody has this, because our root cause troubleshooting, we're going to dive right into it. I know Jim does round numbers. I don't want to do round numbers. So let's do, got 135 feet. What's the head of 135 feet of pipe and baseboard? Copper circuit. He killed it again?
Oh, he's on fire.
You know, I gave a bad example because this is like one of the ones that's in our troubleshooting, but that's okay.
Actually, he's wrong.
Uh-oh. Uh-oh. Shot across the bow. I heard Jim give a shot across the bow.
Everybody's getting it.
All right. Everybody got 8.1 feet ahead, right? Fantastic. That's half of the job you need to size a circulator. The other side would be, what is my flow rate? GPM. So here we go into root cause troubleshooting. This is your boiler system. The space heating right here, your zone valves, that's 100,000 BTU load. Your indirect, the coil in your indirect has the ability to absorb 120,000 BTU. I did not give you a boiler size. You can make it whatever you want, 120, 100, 220, whatever you want to do. This is your call. So you're going to tell yourself what your boiler size is. Your longest heat circuit is 135 feet. Like I said, I just gave away one of the answers. 135, you did the math already. That's 8.1 feet ahead. Your largest heat circuit, so one of these heat circuits has 40,000 BTU on it. But the critical information here is the boiler head drop. This heat exchanger has a 12-foot head drop. This coil in the indirect has a 12-foot head drop. So you need to size P1. So you're going to pick your boiler size, whatever it is. You're going to size P1 and you're going to size P2. Those are the two answers we are looking for. Circulator size for P1 and P2. And let's just simplify this. Everybody's going to pick 120,000 BTU boiler. The boiler will have a 20-degree delta T. So you can use your universal hydronic formula to figure out your flow rate. And that will help you figure out your circulators. You will use page 55 in your TACO book to find your circulator curve chart. It will be the top chart on page 55 is the chart that you're looking for this exercise. Jim and I always have this conversation. Do what you know first. If you're stuck, do what you know first. It may lead you down the path of finding the correct answer. But you're going to have a 120,000 BTU boiler. $120,000 BTU boiler. While they're doing a little bit of math, I'm going to grab a paper towel so I can dry that board.
one answer.
Okay. And that answer is, hold off.
I want a couple more.
Yeah, we got to get some more. All right, so we'll help here a little bit. 20-degree delta T, 20 times 500 is 10,000. 10,000 divided into this becomes this. So we have 12 gallons per minute. That's half of the equation. If you're looking at your circulator chart, you're going to go to 12 on the bottom of that chart. We are nice enough in this example to give you the pressure drop, head pressure drop of the boiler. That's at 12. We're nice enough to give you the pressure drop of the indirect at 12. So your flow rate is 12 GPM. The head pressure drop of the boiler for P1 is 12, and the head pressure drop for P2 is 12. So it's 12, 12. 12 GPM, 12 feet head. What's that equal on that circulator chart? I bet a lot of guys don't have the circulator chart.
That's what I'm thinking.
All right, so let me do this. Everybody's good with the diagram? Let's, Chris, I lost my clicker. Yeah, probably not the best circulator chart I could give you, but look at the lines, not the green ones. You know what? We had one back here. Where is it? Should have had it right there. There we go. There we go. I should have went that way. Sorry. So if we need to overcome 12 feet ahead, we're going to go right here to this line, 12 feet ahead, follow it across, 12 GPM, come straight up, 12 and 12. We're just underneath line number 10, right? If I go to line number 10, I would need a 0012 circulator. And because my rate is 12 and 12, it would be a 0012 circulator for both heat circuits. How many guys got that?
One gentleman changed his answer.
Okay. Okay.
Yeah, not everybody.
No?
No. And one gentleman was confused on the GPM, and I was just typing in the answer as to why. You know, I was just remember it's a 20-degree delta T.
Right. Okay. Well, that's our first one. There'll be more.
There'll be more.
There'll be more.
All right. I mean, we had a 0014, 0015.
15's a little light.
Yeah.
All right. Clean that piece of paper off. We'll do another one here. And based on time, we might have a little homework. Love it. Yeah, right. Imagine. All right, let me get rid of this. Here is the scenario of this one. This boiler was installed recently, and well, we won't go there. Let's just figure it out. 30-degree delta on the boiler. Different. So 30 times 500 is 15,000, right? Boiler loop size. We'd like to know what the piping size is on the boiler. That is a hydraulic separator. That is like closely spaced T's. So the boiler piping, what size would it be? What is the flow rate going to be across the boiler? And what is the circulator size on the boiler side? If you're doing really well, you can cross over to the system side. There's a Takeo circulator there. There are 3 zone valves. Each zone is 40,000 BTU. The longest loop is 135. What size would that circulator be? So for this example, you'll need page 51, 55, and if you have your piping chart from week 1, that would also be good. If you have any questions, send them in. I can easily take this and put it on the board. This is, you know, if you don't know something here, now's the time to ask, because if you leave without that information, you're leaving without that information. So don't hesitate if you have a question. Ask, please. You should give them your phone number, Jim, and they can call in questions.
Oh, one gentleman wants to know, how do you size the boiler loop pipe?
Okay, that's going to be based on that pipe.
Yeah.
Here, you want to take a picture of that, and that'll help you size your boiler loop pipe. And I'm going to go back to that diagram here in a couple of seconds. And I'm back. Okay, what else? You're answering them all with your keys.
No, gentleman had to leave, so you want to know, can he still see this? I'm just letting him know it's recorded. It is being recorded.
Oh boy.
Find it.
Oh boy. Another recording. Anyone have the boiler side done? Okay, good. This is a little easier when we're in the room with you guys to do this. We can float around the room and answer questions, but oh, you guys got Jim smiling again, so I think that's good.
All right, so a gentleman's got the GPM.
Okay, what's the GPM?
8.
Okay, so he took 30-degree delta, right? So 30 times 500 equals 15,000. He's got a 120,000 BTU boiler. Divided by 15,000 equals 8 gallons per minute. So you guys are using the universal hydronic formula here time after time after time. And again, you're going to multiply or you're going to divide. So here we're multiplying. So we know the 8 GPM. Okay, so for that gentleman, I'm going to go to this chart. Actually, what are we doing? What's the wrong way? I want to go to that chart.
Yeah, because he picked an ECM, by the way.
Okay, good. So right there, what is the flow rate for 8 GPM? Is everyone happy with 1-inch pipe? All right, so now we've answered the questions here. The boiler loop size is 1 inch. The flow rate of the boiler is 8 GPM. The circulator for that job would be 1-inch pipe. And you could do that with a 007E.
Nailed it.
All right? You getting any communication on the system side?
Not yet.
Okay. Three zones at 40,000 BTU, 20-degree delta T. Here's 40,000 BTU. What do I do with the comma to get my GPM? Anyone answer that one? Did we lose communication?
No, I think they're thinking.
Okay, good. I think we're going to have a couple of leftovers.
Gonna have a couple leftovers.
Going to have a couple leftovers. We'll do one more after this one. Try to get them out of here at that, you know, I think we're probably touching that hour and a half, right? What do you got?
Our hard cheap is fooling around.
All right. So if I move that comma over, that gives me 4 gallons per minute, right? 4 gallons per minute. How many zones do I have? 3. total flow rate, 12 gallons per minute. Do your head loss, 135 times 0.15 times 0.08 or 04, excuse me. What is my head loss of the longest heat circuit? 135 times 1.5 times 0.04 equals 8.1 feet of head. So go to your circulator chart. You'll probably be on page 55 for this one. And what size circulator do I need to move 12 gallons a minute at 8.1 feet of head?
Below 10.
Beautiful. Okay, excellent. Everyone understand where those numbers came from? And obviously you're in the room, your head would be bobbing right now, or you'd have a glazed over look, and we would know. But since we're looking at the computer, it's a little tough. All right, so let me clean this one off the board. No questions on that one, Jim?
No, sir.
Okay, here we go. Let's get rid of this one. We're going to do one more. It's a long one, but we're going to do it.
Chris, you're on for the next one. Come on.
Okay, and then we'll call it a wrap and pick up a couple for next week, leftovers. Okay. We have done majority of the math here for you. We've done the head loss calculation, so we have measured the heat circuits for each one of the zones, zone 1 through 7. We put the flow rates on there. So sizing of the circulators, you're going to look at 1 through 7. There's the head loss. That's going to be, again, the left-hand side of your circulator curve chart. The flow rate will be the bottom portion of your circulator curve chart. You will use page 51 or 55 to find what circulators this needs to be. If you can size circulators 1 through 7, that would be great. Based on your universal hydronic formula, you have a cast iron boiler. I would like to know what the size of that cast iron boiler is. And then if you really want to go crazy, you can do the pipe sizing to go with that boiler size and the circulator size to go with that boiler. So this will take you a little bit of time. Like I said, we did put majority of it out there for you. It's really just going to be looking at circulator curves and picking circulators. So start that exercise and go from there. You will use the universal hydronic formula on page 48. You will use page 55, that circulator chart at the top, and you may use page 51, depending on if you want ECM circulators or AC circulators. Where are we on time, Jim? So we'll give him a good 5 minutes here.
We got 5 minutes.
Okay, give him a good 5 minutes.
5 minutes.
Clean slate.
Clean slate, baby.
Clean slate.
Chris knows. She knows the answers.
She's working on it over there. I see her.
She knows.
Focused, very focused.
TikTok, 4 minutes.
Okay. Zone 1, 2, 3, 4, 5, 6, and 7. This is 7 feet ahead, 7 feet ahead, 8 feet ahead, 3 feet, 6 feet, 10 feet, and 9 feet. This is GPM. Okay, this is 3.5, 3.5, 3, 4, 2.5, 4.6, or 4.5, and 6 GPM. Okay, and down here, GOPM. That's got to go over a little bit.
All right, we got one guy who jumped in.
Okay, on circulators?
Pick the circulator for all of them.
I think I know what that circulator is for all of them. That means he went ECM.
He did. Would you like to know what he picked?
In a minute or two. What do you got left for time?
Yeah.
3 minutes? 2 minutes?
2 minutes.
2 minutes?
2 minutes. Okay, our high achiever nailed the boiler size and pipe size.
Fantastic. Did he get the circulator size?
No, you didn't touch that.
He's working on it.
He's working on it.
Zipping through.
He probably answered 10 phone calls in between.
Yeah, zipping through.
All right, so another gentleman picked the circulators with one circulator.
He did.
He did.
Wow, wow, good.
Two guys.
All right, so for the 2 guys that picked the circulator, can I guess? 0, 0, 15, E. Covers all of them.
Actually, they went with 007s
7 is very close on a couple.
on a couple.
Yeah, the reason I went with a 15E is because some of these will be at low.
Right.
And I can save more electrical energy when I'm at low. 7E, okay, I'm loving it.
Tighter to that curve.
Yep, we are. We'd be much tighter. But 7E, 15E, golden.
And another gentleman went with DT 2218.
Oh, baby, we love him.
We do like him a lot.
Great. Now, for the AC guys. And I'm going to ask this question, and we did this. So 006B, 006B, 005, 006, 006, 008, 007. How many guys in the audience that are toughing it out with us have ever installed anything on here except maybe a 007 or a 008? If you did this with AC circulators and sized it correctly, these are typical heating zones. This is not like we've made a stretch here. These are typical head drops. These are typical flow rates. They're 25,000 BTU circuits, 45,000 BTU circuits, 30,000 BTU circuits. So they're all legitimate sized circuits. This one down here with 6 GPM, that would be a 1-inch circuit, right? So they're all legitimate circuits, but this is what you would need on the AC side of the circulator world in order to achieve the same job. So these ECM circulators give you a wider window of operation. So let's apply the universal hydronic formula to sizing that boiler. GPM blank times delta T, 20 times 500 equals 10,000. will give me the boiler size. So if I add up 3.5, 3.5, 3, 4, 2, 5, 4, 5, 6 equals 27 gallons per minute. 27 gallons per minute times 10,000 tells me it's a 270,000 BTU boiler. If I have a 270,000 BTU boiler, I would need a 2-inch header. I would need 2-inch near boiler piping. And then to size the circulator, I was waiting for this question. We did not get it. You would need to know the head drop of a cast iron boiler. It's usually 2 to 3 feet. So if you went with 2 to 3 feet of pressure drop on that cast iron boiler at 27 GPM, this boiler would need a 0010 circulator on the boiler circuit, the primary, the secondary circuit on the boiler circuit. It would need a 0010. So that's what that job would look like if you went through every single one of those categories and sized your circulators, sized your piping, sized your boiler piping, sized your boiler circulator to get that 270,000 BTU out of that cast iron boiler up to the header, so those circulators could take that energy and send it through the heat emitters, come back cooler, and be reheated. So that's what that job would look like, breaking it down. So I think we've kind of pushed our time envelope here. We're going to roll a couple of these root cause troubleshooting problems for next week. If anyone has any questions or something that we need to answer, I am just going to flip to the end. So we have the emails on there, so you can either email us or send a question in now. We appreciate everybody hanging in there with us, and
Make sure if anybody did not do their downloads of the handouts, that they do it for next
yeah,
week.
you'll need it for next week because we'll be doing more of the root cause troubleshooting. The most common pages, again, guys, are going to be 48, 51, 55 in that Takeo catalog. They're going to be the ones you're going to use the majority of the time. So if you could get those 4 pages downloaded, that would be great. And
If there anybody's having problems with it, just email me and we'll just email it to you.
okay, yeah, if you don't have it or you can't download it or you're struggling, just send Jim an email, Jay DePalma there at the bottom, wellsdarby.com. Jim will be your instructor next week. I will be out training at another location. So I'm going to sign off and thank you guys for participating. We appreciate it very much. And if you have any additional questions or you're confused or whatever it may be, again, reach out and we'd love to get you up to speed. So thank you again. See everybody next week, 7:30, Wednesday morning. Jim DePalma will be your star instructor. Thank you, everyone.